We've talked about collisions and how momentum is conserved in collisions, but now we want to talk about the different types of collisions we can have, or what can happen when you have a collision. So this first term, we're going to talk about very broadly because we're not talking about energy in this unit. So we're just going to talk about this broadly. But this first one is elastic. And elastic collisions are collisions where kinetic energy is conserved. Now again, we're not talking about kinetic energy in this unit. You don't necessarily know what this is, that's fine. All that I want you to know is elastic collisions where kinetic energy is conserved. And it's when things bounce or change their momentum the most amount possible. The other one is inelastic collisions. And this is where kinetic energy is not conserved. And this is because it's usually lost. And the last one, that's the one that the only reason I'm really bringing this up is because there's a category of perfectly inelastic collisions. And that's where the objects stick together after the collision. And why I'm bringing this up, we're not going to really deal with the distinction other than I'm just going to tell you that we're going to deal with these two situations, elastic and perfectly inelastic. So you might notice this in some of the simulations or things that we do where you might end up creating some inelastic collisions. But for what we're going to worry about, it's either objects stick together or they bounce apart and kinetic energy was conserved. So perfectly inelastic collisions, objects stick together. Elastic collisions, they don't stick together. That's not technically the correct definition. To think of elastic as where they don't stick together, but for sake of this class, that's fine. For sake of intro, that's fine. The last thing I want to mention is explosions, and explosions are perfectly inelastic collisions in reverse. And this is where objects start stuck together and then fly apart. So if you imagine a perfectly inelastic collision, two cars come together and they get stuck together and slide off. Well, if you took a video of that and played it in reverse, it would look like they were traveling together and then fly apart. That's an explosion. It's an example of a perfectly inelastic collision, just reverse of what we usually think of in a collision. So let's do an example and you can see where we care about the fact that it's perfectly inelastic. A 70-kilogram ice hockey goalie catches a 0.15 kilogram hockey puck that was traveling at a speed of 35 meters per second. If the goalie was at rest before catching the puck and there's a negligible friction force between the goalie and the ice, how fast do the puck and goalie move after the goalie catches the puck? So this is a perfectly inelastic collision because the goalie catches the puck and the goalie are stuck together after the collision. So let's draw a diagram for this. So we start off with the mass of the puck is equal to 0.15 kilograms. It's got an initial velocity of 35 meters per second. Then we've got our goalie with a mass of 70 kilograms. And an initial velocity is equal to 0 meters per second. And then afterwards, they're stuck together. So this has a mass equal to mass of puck plus mass of goalie. And it has a final velocity that we are trying to solve for. So there's two ways of looking at this. One, we could say that the puck and the goalie both have the same velocity afterwards, or what I tend to like to do is just say it's a single object with a combined mass of those two. So we're going to start with our conservation of momentum. The initial momentum equals the final momentum. The initial momentum is mass of the puck plus the velocity of the puck plus the mass of the goalie plus the initial velocity of the goalie. And that will equal the final mass times the final velocity. Again, because the goalie's at rest, we can zero that out. And we end up with mass of puck times initial velocity of the puck divided by m is equal to our final velocity, which is equal to the mass of the puck times the velocity of the puck divided by the mass of the puck plus the mass of the goalie, because again, that's what our m is. Velocity is equal to 0.150 kilograms times 35 meters per second divided by 70.15 kilograms. You'll see that the kilograms will cancel. You'll get some other number. It should be rather small. Let's see, this would be half times 0.1. So it's going to be around 0.06 maybe. Eyeballing, so 0.06-ish about. You can plug it in if you're unsure if you did the calculation right. Ask me in class, but I'm going to jump into the next example here. Example 2, two toy cars collide head-on and then rebound in opposite directions on a frictionless surface. Car 1 has a mass of 3.35, initial velocity of 2. Car 2 has a mass of 0.5, initial velocity of negative 0.5. After the collision, car 1 recoils with a velocity of 4 meters per second. What's the final velocity of car 2? So this is an example of a perfectly elastic collision. You won't know how we're able to evaluate that, but like I said, anything that's not perfectly inelastic, we're going to assume is elastic. So V of car 1 initial is 2 meters per second. And V of car 2 initial is negative 0.5 meters per second. Car 1 has a mass of 0.35 kilograms. Car 2 has a mass of 0.5 kilograms. After the collision, car 1 recoils in the opposite direction. We saw that here. So we know it's going to be backwards. So V1 is equal to negative 4 meters per second. This is still M1. And we're looking for V2. And the nice thing here is we don't necessarily have to know that this went in the opposite direction. We'll find that when we do the math, this will be a positive or negative number. And depending on the sign of that, we'll know which direction it traveled, either in the positive or the negative. So the net initial momentum has to equal the net final momentum. So that's M1 V1 naught plus M2 V2 naught equals M1 V1 plus M2 V2. We're solving for V2, so that will be M1 V1 naught plus M2 V2 naught minus M1 V1 divided by M2. If you need to pause to check that math or to follow that algebra, feel free to, or ask in class. M1 is 0.35 kilograms. V1 is 2 meters per second. M2 is 0.5 kilograms. V2 naught is negative 0.5 meters per second minus 0.35 kilograms times negative 4 meters per second all divided by 0.5 kilograms. And that's going to be our V2 final. I'll plug these in real quick just so we've got a number, because that's something I can't estimate quickly in my head here. So 0.35 times 2 plus 0.5 times negative 0.5. That looks right. Plus 0.35 times 4, because there's two negatives, so I'm canceling that out. 1.85 divided by 0.5, so that'll be 3.7 meters per second. And again, because it's a positive number, we know that it is to the right. So that's what we have here. Again, same idea as before, conserving momentum. It's just whether or not the objects stick together or whether they bounce off.